Hello all, my name is Christian Schillinger, and I'd like to introduce the project of trajectory optimization that I worked on with my partners Susan Nee and Max Thomsen. In this project, we present an investigation into the overall effectiveness of different frameworks for trajectory planning and control of a quadrotor in a complex environment. We determined that because there is a variety of ways that information about the environment can be passed to a quadrotor, certain strategies are likely better than others in specific applications. We present two solutions. The first was the use of direct collocation for nonlinear programming when ground truth information about the environment is available. And the second is a search-based trajectory planning algorithm that functions by creating a cost map given vision information about the environment. In our analysis, the effectiveness for a planning approach is determined by energy consumption, computation cost, optimality, and sensor modality. So moving into our first approach. For direct collocation, we followed the equations set out in the textbook. We also used classes imported from Drake libraries, most notably the Quadrotor plant class and the direct collocation class. Both of these imports allowed us to abstract away the dynamics of the quadrotor and implement a clean and fast collocation algorithm. As you can see on the right, the additional constraints beyond the dynamics on the collocation and breakpoints were maximum and minimum rotor thrust values, minimum Euclidean distances between the quadrotor and the cylinder obstacles, minimum distance from the ground to account for potential of large pitch and roll values near the ground, and the initial and final states of the quadrotor. The running cost was set as the sum of the squares of the rotor thrust values to simulate minimization of energy consumption, and the final cost was set as the overall flight time. The square of the rotor thrust values were used to take into account the relatively linear relationship between thrust and rotor speed, and the nonlinear relationship between rotor speed and power consumption. The output of this algorithm tends to appear ideal. The quadrotor does not make sharp turns, fly too fast, or waste energy ascending or descending. However, this algorithm requires prior ground truth knowledge of the map, which would be very difficult to determine outside of the simulation. This is why and when we moved on to our second technique.
In order to not depend on a prior map of the environment, we welded a camera in our simulation that is able to capture RGB and depth images of the scene. The vision data then can be used to construct a cost map to use in lieu of the prior map. Our environment was constructed to allow simple color segmentation to create a mask of which pixels on the RGB image correspond to cylinders. The mask can then be applied to the depth image, and using the pinhole camera model, the masked depth pixels are projected into world coordinates, resulting in the 3D point cloud. To obtain a bird's eye view of the scene, the z-coordinate of the 3D points can be removed to create a 2D cost map. Then A-star search is performed in the 2D cost map to find a path between the start and goal positions. The cost map is inflated to account for the width of the quadrotor to avoid crashes. For reference, this is the found path overlaid in the original cost map, and you can see the buffer between the quadrotor and the cylinders that the inflated cost map provided.
The A-star search algorithm outputs a pair of xy points, and we use the quadrotor's differential flatness property to back out a trajectory composed of all 12 states in time. First, though, we have to smooth out the path in order for differential flatness to work properly. We use a convolution to smooth out sharp edges in the path and, optionally for cases where we want to start and end at a hover, we interpolate new points along the path so that the velocity trajectory is more continuous and we effectively reduce the velocity at the endpoints. We can set the height to 0 and the yaw to a constant, as these will not affect our collision avoidance, and then we can generate a full 12-state trajectory. With our full state trajectory, we can use a finite horizon formulation of LQR to control the quadrotor. These two images show two different trajectories generated from A-star and differential flatness, in pink, overlaid with the quadrotor's tracking from a simulation, in blue. They are nearly indistinguishable in the first image and very similar in the second. In this example, the quadrotor begins with a non-zero velocity and follows the trajectory with a constant velocity until the end position. In this example, the quadrotor follows the same xy trajectory with the same total duration, but with a smoothed out velocity profile, beginning with 0 initial velocity. The path following and collision avoidance is nearly identical, but the second example is able to demonstrate 0 velocity initial conditions.
After running our direct collocation A-star search with LQR solutions and many different random environments, we gain a lot of insight on the benefits and drawbacks of the two approaches. For direct collocation, we are directly able to add constraints on the optimization problem to account for energy consumption and inherently encounter vehicle dynamics, which provides a smooth trajectory that can be tracked naturally, as shown in the image to the right compared to A-star in the same environment. However, with our formulation, we required a prior map of the environment in order to obtain a global path. But even so, since direct collocation is solving a nonlinear optimization problem, there's no global optimum guarantees, and there were many instances where the solver failed to find a solution. Reducing failure rate meant an increase in runtime to a point where it's no longer realistic for online planning. A-star search and LQR control does not require a prior map and guarantees to find an optimal solution based on distance within the camera's field of view, but it's more difficult to not only add energy constraints, but also consider vehicle dynamics, which results in trajectories with sharp corners that require unnatural motion to track and will require high energy consumption. Though this approach will never have direct collocations issue where potentially no solution is found, LQR can't perfectly track the trajectory as shown in the image to the right, which could cause the quadrotor crash into a cylinder.
Future work for this project could include trajectory optimization for a multimodal vehicle, for example, a dual quadrotor wheeled vehicle capable of switching between flying and driving. In this case, the optimizer would additionally have to decide when and where to switch between modes based on the environment and cost functions. A slight extension to this project would be navigating through an unknown environment, where the camera is attached to the quadrotor frame and mapping and planning is done online. Additionally, in order to improve the tracking of a trajectory, the differential flatness property could be further exploited to generate a nominal input trajectory.